All right, buckle up, everybody, because today we are diving deep, deep into the world of fracking fluids. You hear about fracking all the time, but have you ever wondered what actually goes into those fluids? Like what makes them tick, how they work, why they're so crucial to the whole process?
It's like, it's almost like a magic potion, right? There's so much going on in there.
Exactly. And we've got the perfect source to quench your curiosity. We're cracking open a technical chapter all about the components that make up these remarkable fluids.
Think of it like a recipe book, but instead of flour and sugar,
Yeah.
you got polymers and cross-linkers and a whole lot of chemistry.
Exactly. It's going to be a wild ride. And by the end of this deep dive, you'll know exactly what factors those engineers consider when they're choosing a fluid.
Yeah, like tailoring a suit, but for a fracture thousands of feet underground.
That's a great analogy. So before we get all tangled up in polymers, let's start with the basics. What exactly is hydraulic fracturing, and why does it need these super specialized fluids?
So fracking, as it's often called, is essentially um, pumping fluid under immense pressure to crack open rock formations deep, deep underground.
Okay, so we're talking like controlled rock splitting, but on a massive scale.
Exactly.
Mm.
And these cracks, they create pathways for the oil and gas trapped in those rocks to flow.
Okay, I'm starting to see the picture here, but why can't we just use like regular water? Why do we need these fancy fluids?
Because we're dealing with a very specific environment down there. These formations, they're deep underground, often contain a whole ecosystem of minerals, fluids, and you need a fluid that's, well, engineered to do the job right.
Okay, so that makes sense. But speaking of water, I mean, we all know it's essential, right, for pretty much everything. But when it comes to fracking, it's not as simple as just grabbing a bucket from the nearest lake.
Oh, absolutely not. Water quality is paramount. For standard fracking jobs, the water needs to be filtered down to 50 micrometers.
50 micrometers, that's like incredibly fine.
It is. To give you an idea, a human hair is about 70 micrometers wide.
Wow. So we're talking like filtering out particles that are smaller than a dust mite.
And for some specialized fracking jobs called frac packs, the filtration level needs to be even finer, down to 2 micrometers.
Okay, now that's just getting ridiculous. But it makes sense. I mean, you don't want any gunk clogging up those carefully created fractures.
Exactly.
Now, I've also heard about using flowback water, the water that returns to the surface after a frac.
Right.
Is that a thing?
Yes. Reusing flowback water is becoming increasingly common. I mean, it helps conserve freshwater resources, reduces the need for
You
disposal.
doing, right.
Well, not always. It comes with its own challenges. Flowback water can contain leftover breaker chemicals, and those can interfere with the new fluids.
So it's kind of like you're trying to bake a cake in a bowl that still has traces of the last batch of cookies.
That's a great analogy.
Okay, so it's a balancing act, trying to be eco-friendly while also making sure the fluid actually does its job. All right, so we've got our super clean water. What's the next ingredient in our fracking fluid recipe?
Clay control.
Clay control. What's that all about?
So when water interacts with certain minerals in the rock formation, those minerals can, like, swell and shift, potentially blocking the flow of oil and gas.
Oh, I see. So it's like you're trying to build a house on shifting sand.
Exactly. You need a solid foundation, and that's what clay control agents provide.
Okay, that makes perfect sense. And I've read that potassium chloride, KCl, is like the go-to for this.
It is. KCl is incredibly effective at stabilizing those clays. It's far more effective than, say, sodium chloride or calcium chloride.
Uh-huh.
There are organic clay stabilizers out there, but they often underperform at the concentrations we need.
Interesting. So it's like trying to build a brick wall with glue instead of mortar.
Exactly. It's just not going to hold up.
Okay, so we've got our clean water, we've got our clay control sorted. What's next?
Now, things start to get a bit slippery. Literally, it's time to add friction reducers.
Friction reducers. I can already see why this would be important. I mean, you're pumping fluid thousands of feet underground through these narrow fractures. That's going to create a lot of friction.
You got it. That friction takes a lot of energy to overcome, makes the process less efficient, puts more stress on the equipment. Friction reducers, as the name suggests, help minimize that friction, making everything run a lot smoother.
Okay, that makes perfect sense. Now, I know there are different types of friction reducers.
There are.
It's like a polymer party down there. Can we break down the key differences between them and when you might choose one over another?
Absolutely. You can think of it like choosing the right type of oil for your car engine.
Yeah.
All do the same basic job, reduce friction, but they have slightly different properties.
Okay, I like that analogy. So, like, what's the most common friction reducer?
The workhorse, you could say, is partially hydrolyzed polyacrylamide, or PHPA for short.
HPA, got it. And why is it so popular? What makes it stand out?
It's just a great all-rounder. It strikes a good balance between performance and cost-effectiveness.
Okay, so reliable and affordable, like the Toyota Camry of friction reducer.
Exactly. It gets the job done.
All right, I can get behind that. Now, what about some of the, like, the more specialized friction reducers? When would you pick something else over PHPA?
Well, let's take polyacrylamide, or PAM. Now, this one, it's incredibly tough. It can actually gel strong hydrochloric acid, which is a very corrosive substance.
Wow, okay, so it's like the heavy-duty truck of friction reducer.
Exactly. Powerful, but you need to know what you're doing.
Right. And what about some of the other ones I've heard about?
Well, there's polyacrylic acid, or PAAC. It's very versatile, actually used in everything from diapers to cosmetics.
No way. So it's like a polymer with a side hustle that's got a whole other career path?
It does.
Yeah.
But it has a bit of a sensitive side. It's susceptible to certain ions, especially in hard water, which can limit its effectiveness in some fracking scenarios.
Ah, okay. So picky eater. No, what was that other one?
Oh, acrylamidomethyl propane sulfonate, or AMPS.
AMPS, right. Now that one sounds like it's ready to tackle just about anything.
It is. It handles tough conditions like hard water, high temperatures, even the presence of CO2. It can act as a scale inhibitor, too, preventing mineral buildup.
So it's like a multitasker.
Oh, absolutely.
Hmm.
And you might be surprised to learn that it's also used in AKG gel. You know, the stuff they put on your chest for heart monitoring.
No way. That's incredible. From high-tech medicine to, heavy-duty oil field operations.
It's a versatile molecule.
It really is. Okay, so we've successfully made our water super slick. What's next on our fracking fluid adventure?
Now it's time to thicken things up. We're talking gelling agents.
Okay, gelling agents. So these are what give the fluid the right consistency.
Exactly. They literally thicken the fluid. Think of it this way. During fracking, we're not just pumping fluid into the rock. We're also pumping in these tiny particles called proppants.
Proppants, right. They're like sand or ceramic, right? And they hold open those fractures we created.
Exactly. And the thicker the fluid, the better it is at carrying those proppants deep into those fractures.
Ah, I see. So if the fluid was too thin, those proppants would just settle to the bottom?
Exactly. And our fractures would close back up. No good.
Okay, that makes sense. So the gelling agents are like what? Like the heavy-duty trucks carrying those proppants to their destination?
Yeah, a perfect analogy. And there's another key reason why viscosity, that thickness, matters. Fluid loss control.
Right, because we don't want all that expensive fracking fluid just leaking off into the surrounding rock.
Exactly. We need it to stay in the fractures where it's needed. And higher viscosity helps minimize that leakage.
So it's like what, using a thicker syrup versus a thin juice? The syrup's not going to drip as much.
Precisely.
Okay, so it's all about maximizing efficiency, making sure that fluid does its job. Now, I did some reading on this, and I came across this term molecular weight, and it seems to be like tied to viscosity.
It is. You're on the right track.
Can you explain that?
So the gelling agents we use are polymers. Think of them like long chains of molecules, like strings of beads.
Okay, I'm visualizing it.
The longer and more tangled those chains are, the thicker the fluid will be, like comparing a bowl of spaghetti to a bowl of rice.
Okay, yeah, the spaghetti's definitely more tangled.
Exactly. Engineers use the concepts of critical overlap concentration, or C, and critical entanglement concentration, or C, to figure out the ideal concentration.
CNC, got it.
They want those polymers tangled enough to make the fluid viscous, but not so tangled they clump together and cause problems.
Right, so it's all about finding that sweet spot, that perfect balance.
Exactly. And when it comes to gelling agents, there's one superstar that really stands out. Guar gum.
Guar gum. Wait, isn't that used in food?
You've got it. It's a natural polymer derived from the guar bean. You'll find it in ice cream, toothpaste, cosmetics, and, of course, fracking fluids.
Wow, that's amazing. From your toothpaste to, a mile underground. So what makes guar gum so special for fracking?
Its unique chemical structure. Guar has special sites along its backbone that allow it to be both cross-linked, meaning those polymer chains can connect to each other to create a stronger gel, and it can be easily broken, making it easy to clean up.
So it's like, what, a transformer molecule?
Mm-hmm.
It's tough when it needs to be, but it can break apart easily when the job's done.
That's a great way to put it.
Now, you mentioned derivatives of guar gum earlier. What are those all about?
Think of them like Specialized versions of guar gum, each tweaked slightly for different applications. For instance, there's hydroxypropyl gar, or HPG.
HPG, okay.
It's more stable at high temperatures, so good for those hotter reservoirs.
It's like the gargum family has a member for every occasion.
That's right. And besides GARG and its derivatives, we have other gelling agents like HEC and CMHEC, which are actually derived from cellulose.
Cellulose. Isn't that like the stuff that makes up plant cell walls? So we're essentially taking a component of plant matter and using it to engineer fractures deep underground.
Exactly. And they're particularly useful in applications where conductivity, the ability of the fracture to allow fluids to flow freely, is crucial.
Oh, so they're like the eco-friendly option in the gelling agent world.
That's one way to think about it.
Now, even though they're both derived from cellulose, HEC, and CMHEC, they have some, like, key differences, right?
They do.
Okay, I'm curious about that.
Well, for starters, they each handle fluid loss in their own way. HEC relies on what we call viscosity-controlled fluid loss.
Okay.
It's like sealing a crack with thick syrup.
Oh,
The syrup's own viscosity prevents it from leaking out.
makes sense.
CMHEC, on the other hand, is capable of something called cross-linking, which means those polymer chains can connect to each other, creating a stronger gel.
So it's like CMHEC has this, like, hidden superpower that HEC doesn't possess.
Exactly.
And then there's this whole other type of gelling agent, viscoelastic surfactants, or VESs. Now, these don't rely on polymers at all, right?
You're right. Instead of long polymer chains, VESs rely on the way their molecules arrange themselves, forming these microscopic structures called micelles.
Micelles, okay, I'm trying to picture this.
Think of it like a bunch of tiny soap bubbles clumping together.
Okay, I can kind of see that.
So because they don't rely on polymers, VESs are very clean, cause minimal damage to the proppant pack's conductivity.
So they're like self-assembling nanomachines, creating viscosity through, like, sheer molecular ingenuity.
Exactly. But like any powerful technology, they have a potential drawback.
Oh, what's that?
Well, VESs can sometimes react badly with certain reservoir fluids, disrupting the flow of even high-quality hydrocarbons.
So they're so good at cleaning things up that they can sometimes clean up a little too well.
That's one way to put it. Now, besides all these water-based gelling agents, we also have oil-based fluids.
Oil-based fluids, really? I mean, why would you use those if you have all these water-based options?
Good question. Oil-based fluids are still used today for specific situations, especially for water-sensitive formations. Formations that would be damaged by contact with water.
Ah, okay. So it's all about choosing the right tool for the job.
You got it.
But those oil-based fluids, I mean, I bet they're a lot more complex than they were back in the early days of fracking.
You're absolutely right. Modern oil-based fluids utilize what we call aluminum phosphate ester chemistry to create that gel. Relies on a similar mechanism to VESs, actually, with those self-assembling micelles.
Wow. So both oil-based fluids and VESs are harnessing the power of those tiny, molecular structures. That's pretty cool, but I'm guessing oil-based fluids have some challenges too.
Of course. They can be very sensitive to water. Any excess water in the oil can mess with the viscosity, cause stability problems.
Oh, right, like trying to mix oil and water. They don't exactly get along.
Exactly. And there can also be compatibility problems with certain types of crude oil.
Ah, okay, so it's not a one-size-fits-all solution, but still a valuable tool in the fracking toolbox. All right, so far we've talked about water, clay control, friction reducers, gelling agents, even touched on oil-based fluids. What else is there?
Well, now that we have all our basic ingredients in place, it's time to think about how we can really fine-tune those gels, make them work even better.
Okay, now we're talking. What's the secret ingredient here? What's going to take these gels to the next level?
Crosslinkers.
Crosslinkers. Okay, tell me more.
Imagine you have a bunch of loose threads. They're strong individually, but they're not connected. Now imagine weaving those threads together into a fabric. That fabric's going to be much stronger, more resilient, and that's essentially what crosslinkers do to our gelling agents.
So we're basically taking a bunch of loose spaghetti strands and turning them into a lasagna sheet, much more structured and robust.
You got it. And the most commonly used crosslinker is borate. It's like the duct tape of the fracking world. Readily available, cost-effective, and it works beautifully with guar gum.
Okay, borate, got it. And what makes borate so special?
Well, one thing is that its cross-linking action is dependent on pH.
So you can, like, control how much cross-linking happens by adjusting the acidity or alkalinity of the fluid?
Precisely. It's
Yeah.
like having a dimmer switch for viscosity.
Ah.
And borate has another trick up its sleeve. It can actually break apart under high stress, like when the fluid's being pumped down the well, and then reform quickly once the stress is removed.
Wow, so it's constantly doing this little dance, breaking apart, coming back together. That's really cool. But I'm guessing borate's not perfect for every situation, right?
Of course not.
Mm.
One limitation is temperature. Above 250 degrees Fahrenheit, it starts to lose its effectiveness.
Ah, so for those hotter reservoirs, we need something a bit more heat resistant.
You got it. That's where metallic crosslinkers come in, typically using titanium or zirconium. And get this, they were initially developed for creating explosive gels.
Whoa, that sounds a bit intense.
They are powerful. They create very strong, very rigid gels, which are great for those high-temperature environments.
But with that extra strength, I imagine there's got to be a drawback, right?
You're right. Those strong bonds formed by metallic crosslinkers can be susceptible to what we call shear degradation.
Yeah.
Basically, they can break under high stress, and they don't reform as easily as borate crosslinks.
Ah, so it's like comparing a rubber band to a piece of string. The rubber band can stretch and bounce back, but the string, it'll just break.
A great analogy. And another thing to consider with metallic crosslinkers is that because those bonds are so strong, they can lead to more damage to the proppant pack once the gel is broken down.
So it's a trade-off then. Higher viscosity and temperature stability, but with a potential for lower conductivity in the end.
Exactly.
It's all about choosing the right tool for the job and understanding the pros and cons of each option. Okay, so we've built our perfect gel. It's down in the well. It's done its job.
Yep.
What happens next?
Well, that's where things get really interesting.
Okay, I'm intrigued. Tell me more.
Our carefully crafted gel has done its job, but now we need to break it down. We need to allow the oil and gas to flow freely. And to do that, we need the cleanup crew.
Breakers.
Breakers, that sounds intense.
They are. And that's where we'll pick up in part 2 of our deep dives into fracking fluids. Stay tuned.
All right, welcome back to the deep dive. We're smack dab in the middle of our fracking fluid exploration, and last time you left me on a bit of a cliffhanger with this whole breakers thing. So spill the beans. What are these mysterious breakers all about, and why are they so important?
Okay, so remember all that work we did to create the perfect gel? It's tough. It carries those proppants, controls fluid loss. It's the superhero of our operation down there. But once the fractures are created, its job is done.
Right.
And now we need those fractures to be nice, open pathways for the oil and gas to flow, and a thick gel is just going to get in the way. That's where breakers come in. They break down those polymer chains, thin out the gel, and allow the oil and gas to flow freely. Okay, so they're like the after-party cleanup crew, making sure everything's spick and span before the guests arrive.
Exactly. And just like with any good cleanup, you need the right tools for the job. In the world of fracking, those tools are chemical breakers.
Chemical breakers.
Yeah. And there's a surprising amount of science that goes into making sure they do their job effectively.
Okay, I'm intrigued. So, what are some of the challenges when it comes to breaking down these fluids?
The biggest challenge is timing. Ideally, we want the breaker to be completely inactive during the fracking process itself. We don't want it interfering with the gel's performance while it's busy creating those fractures.
Right. Imagine if the cleanup crew started packing up the decorations before the party was even over.
Exactly. It'd be chaos. But then, as soon as that fracking is done, we want those breakers to, snap into action.
Right. We need that gel to break down quickly and efficiently so those fluids can flow back up to the surface and bring that oil and gas with them.
It's all about timing.
Okay, so timing is crucial. But how do you even control that? I mean, we're talking about fluid traveling down a long well bore, then into these fractures, thousands of feet underground. How do you get those breakers to activate at just the right moment?
That's the million-dollar question. It's tricky. One of the key factors that influences breaker activity is temperature. And as you mentioned, the temperature of the fluid changes dramatically as it travels from the surface equipment all the way down into those fractures.
Right, because those deep rock formations are naturally much hotter than the surface.
Exactly. So we're dealing with this dynamic environment where the temperature is constantly changing, and we need those breakers to activate at just the right temperature.
Gotcha.
And to make things even more complicated, different types of breakers respond to temperature in different ways. Some are more active at lower temperatures, while others need a certain amount of heat to really kick in.
Okay, so it's like having a toolbox full of different wrenches, each one designed for a specific bolt size.
That's a great analogy.
You wouldn't use a tiny wrench to try to loosen a huge bolt.
Exactly. So engineers have to carefully select the right type of breaker based on the expected temperature profile of the well.
I see, I see. And I'm guessing they also have to consider the type of gel they're using, because some gels are probably easier to break down than others, right?
Absolutely. You're exactly right. Some gels are inherently easier to break down than others. Like gar-based gels, for example, they tend to be relatively easy to break. It's like, breaking a cookie, it crumbles easily. But some of those synthetic polymers, they can be much more stubborn, like trying to break a hard candy. You need a more forceful approach.
Right, so it's like a matching game pairing the right breaker with the right gel to make sure we get a clean and efficient breakdown. Okay, I'm ready to dive into the different types of breakers. What are our options here?
All right, so we've got three main categories of breakers: oxidizers, acids, and enzymes. Each one works a little differently to break down those polymer chains.
Okay, let's start with oxidizers. They sound pretty intense.
They are. Oxidizers, like persulfates and peroxides, they're like the demolition crews of the breaker world.
Demolition crews?
Yeah, they generate these highly reactive molecules called free radicals, basically tiny wrecking balls at the molecular level.
Okay, so they just go in there and start breaking things apart.
You got it.
Yeah.
Those free radicals attack the polymer chains, break them down into smaller pieces, which lowers the viscosity of the fluid.
So very effective, but I'm guessing not very specific.
They're catching on. Oxidizers will react with pretty much anything they come into contact with, including the stabilizers that we added to protect our gel. It's like sending a demolition crew into a building without telling them which walls to tear down.
Yikes, that sounds a little chaotic. So, any downsides to oxidizers besides the whole, demolition crew gone rogue thing?
Well, one thing to keep in mind is that they can leave behind what we call residual sugars as they break down those polymer chains.
Residual sugars. Wait, like the stuff we put in our coffee?
Not exactly the same, but similar in the sense that they can be sticky, gooey, and as those residual sugars sit in the warm reservoir, they can react and form these insoluble precipitates.
Insoluble precipitate.
Yeah, basically solid deposits that can clog up the pores in the rock, hinder the flow of oil and gas.
Oh, I see. So it's like spilling syrup on your kitchen counter and letting it dry. It's going to be much harder to clean up later.
Exactly.
So it's crucial to get those fluids flowing back to the surface ASAP after the fracking is done, right? Get those sugars out of there before they cause trouble.
You got it.
Okay, so oxidizers are powerful but need to be used carefully. What about acids? They sound a bit less intimidating, but, still pretty potent, right?
Well, acids are definitely powerful. They work by attacking the polymer chains a little differently than oxidizers, disrupting the chemical bonds that hold those chains together.
So acids are like the solvent cleaners of the breaker world.
That's a good way to put it.
But they're also less selective, right? They can react with, a wider range of materials in the rock formation, potentially causing some unintended consequences.
Right, acids can dissolve certain minerals in the rock, which can alter the permeability of the formation.
So acid's another powerful tool that needs to be used with caution. What about enzymes? Now, those seem like a gentler approach, right?
Enzymes are like the skilled surgeons of the breaker world.
Okay, I like that.
They're incredibly specific in their actions, targeting only the bonds they're designed to break. They work by acting as catalysts, which means they speed up chemical reactions without being consumed in the process. They're proteins, actually found in nature. We use them to digest our food, and some are incredibly effective at breaking down specific types of polymers.
So they're like a key that fits perfectly into a lock, only that specific key can open that specific lock.
Exactly.
So enzymes are very precise and efficient. But I'm guessing they have some limitations too. What are we looking at here?
Well, one thing is that enzymes are much more sensitive to their environment than those chemical breakers.
Okay, how so?
Well, they operate best within a fairly narrow temperature range, typically below 150 degrees Fahrenheit. Above that temperature, they can start to break down themselves and lose their effectiveness.
Ah, so enzymes are like the Goldilocks of breakers, huh? They need everything to be just right.
Yeah, exactly.
Not too hot, not too cold.
And not too acidic or alkaline either. They're also sensitive to pH, just like those crosslinkers we talked about earlier.
So while enzymes offer this very precise and environmentally friendly approach to breaking down those gels, they're not always the right choice for every situation. It's all about considering the specifics of the well and choosing the breaker that's best suited for the job.
You got it. Choosing the right tool from your toolbox, consider what you're trying to achieve, and pick the tool that's going to get the job done most effectively.
Well, this has been a fascinating journey into the world of breakers. I had no idea there was so much science involved in, simply breaking down a gel.
It really is all about understanding that delicate balance of chemistry, temperature, and timing.
It really highlights the importance of, careful planning and execution at every stage of the fracking process. Now, we've covered the main components of these fracking fluids: the water, the clay control, friction reducers, the gelling agents, cross-linkers, now breakers. Anything else we need to add to our recipe here?
There are a few more ingredients that play important, albeit less prominent, roles in our fracking fluid concoction.
Okay.
Think of them as the supporting cast,
hmm
the ones that help ensure everything runs smoothly.
Okay, I'm ready for the grand finale. Let's dive into those final ingredients in part 3 of our fracking fluid deep dive. All right, welcome back to the deep dive.
We've journeyed through the main components of fracking fluids, from the water and the clay control to those powerful breakers, the ones that take apart the gel when it's done its job. But I know there's more to the story, right? Like any good recipe has those, extra ingredients that give it that perfect finishing touch. You're absolutely right. We've talked about the stars of the show, but now it's time to give some credit to the supporting cast.
The supporting
Yeah,
cast.
the additives, they might not be as glamorous, but they play a crucial role in making sure our fracking fluid performs at its best.
Okay, I'm ready for this behind-the-scenes look at the unsung heroes of fracking fluids. So, what are some of these essential additives?
Well, let's start with viscosity stabilizers.
Viscosity stabilizers.
Yeah, their job is to keep that gel thick and strong, even when temperatures start to rise, deep down in the well.
So they're like the heat shields for our delicate polymer chains,
Yeah.
protecting them from those scorching reservoir temperatures.
Perfect analogy. And one of the most commonly used viscosity stabilizers is actually something you might be familiar with.
Methanol.
Methanol. Wait, isn't that like the stuff that can make you go blind if you drink it?
It is, but don't worry, we use it in very low concentrations in fracking fluids, and it serves a very different purpose here. Okay, good to know. So methanol helps keep those gels from thinning out when things get hot. Are there other viscosity stabilizers?
Yeah, another common one is sodium thiosulfate. It acts as an antioxidant, meaning it neutralizes those pesky free radicals.
Free radicals, right, the ones that can attack the polymer chains.
Exactly, and
Yeah.
weaken the gel. Think of sodium thiosulfate as a bodyguard, protecting those polymers from harm.
So it's like having a molecular security detail, making sure those polymers stay in tip-top shape.
Exactly.
And what's even better, sodium thiosulfate is much safer to handle than methanol.
Yes. Much safer.
All right, viscosity stabilizers, check. What's next on our additive adventure?
Next up, we have buffers.
Buffers.
Yep. Might not sound as exciting as, viscosity stabilizers, but they play a critical role in maintaining that delicate pH balance of our fracking fluid.
pH balance. Okay, now that sounds familiar. It's like what they talk about in the skincare commercials, right? Keeping your skin at the optimal pH level.
Exactly. pH is just a measure of acidity or alkalinity. And just like our skin, fracking fluids have an optimal pH range where they perform their best. Different stages of the fracking process require different pH levels, and buffers help us maintain those levels.
Okay, so they're like the pH regulators, making sure the fluid is always in that Goldilocks zone, right?
Yeah,
Not too acidic, not too alkaline, but just right.
exactly. And buffers are especially important when it comes to controlling that cross-linking process.
Right, right. Those cross-linkers we talked about earlier.
A lot of them are sensitive to pH. If the pH isn't just right, the cross-linking might not happen as it should, and our gel won't be as strong.
It's like baking a cake, right? If you don't add the right amount of baking powder, it won't rise
That's
properly.
another great analogy.
So buffers help ensure that all the ingredients in our fracking fluid are, working together in harmony. Now, what about surfactants and mutual solvents? Those sound like they belong in like a cleaning product aisle, not a fracking operation.
Uh-huh. You might be surprised. Surfactants are essentially wetting agents.
Wetting agents.
Yeah. They reduce the surface tension, which allows fluids to spread and penetrate more easily.
Okay.
Imagine trying to wash greasy dishes without soap.
Ugh, yeah, that's no fun.
It's a lot harder to get the water to spread and do its job. Surfactants are kind of like the soap in our fracking fluid.
Oh. So they help that fluid flow more easily through those tiny cracks in the rock formation.
Oh, exactly. And mutual solvents, their job is to help different fluids blend together smoothly.
Oh, okay.
Remember how we talked about oil-based fluids?
Right.
Well, sometimes we need to use a combination of oil-based and water-based fluids in the same fracking operation.
Okay, I see.
And that's where mutual solvents really come in handy. They act as a bridge between those two worlds,
Mm.
ensuring everything mixes together smoothly and efficiently.
So they're like the diplomatic core,
Yeah.
making sure everyone gets along.
You got it. And surfactants, they play an especially crucial role in dry gas wells.
Dry gas wells.
Yeah,
Mm.
because the water in the fracking fluid can actually create what we call a water block.
A water block.
Yeah, it prevents the gas from flowing freely. It's like trying to pour water through a sponge that's already saturated. The water just sits on the surface.
Right. It can't go anywhere.
Exactly. And surfactants help break down that water block, allow that gas to flow.
So they're like the uncloggers, making sure those pathways stay open for the gas. Okay, surfactants, mutual solvents, check. What else do we have?
All right, we're almost there. Last but not least, we have biocides and bactericides.
Biocides and bactericides. Okay, those sound a bit intimidating. What exactly do they do?
Don't worry, their job is to protect, not to harm. Think of them as the sanitation crew of our fracking operation.
Okay, sanitation crew. Got it.
Yeah, their job is to control the growth of microorganisms, like bacteria and fungi, that can cause problems with our fluid.
Wait, bacteria and fungi deep underground.
You'd be surprised. Those little guys are everywhere, and they can cause big problems if we let them get out of control. Some of them actually produce enzymes that can break down the polymers in our gel, basically turning our carefully engineered fluid into a watery mess.
Oh, wow. So it's like having a tiny army of saboteurs working against us.
That's one way to put it. So biocides and bactericides are like our defense system, keeping those microbial troublemakers in check.
And they're not just protecting the fluid itself, right?
Right. They also help prevent harmful bacteria from getting into the reservoir itself.
Okay, so biocides and bactericides are like the guardians of our well, making sure everything stays clean and healthy down there.
You got it.
Wow, we've covered a lot of ground in this deep dive into fracking fluids. From the basic ingredients to the complex chemistry of cross-linking and breaking. We've even explored those unsung heroes, the additives. It's amazing how much science and engineering goes into creating this, seemingly simple fluid.
It's truly a testament to human ingenuity, our desire to unlock those resources in a safe and efficient way. And as technology advances, we're constantly learning new ways to optimize these fluids and minimize their impact on the environment.
Yeah, it's definitely an exciting field to be in, that's for sure. So as we wrap up here, I'm curious, what's the most surprising thing you've learned about these fracking fluids over the years?
What always gets me is just the delicate balance of all the components. It really is like this carefully choreographed dance where every ingredient has its role to play, and the timing of each step is crucial. Getting it right requires this deep understanding of chemistry, physics, geology, engineering, and it's a constant learning process.
It really is a reminder that even the simplest things, like the fluids we use to extract oil and gas, can be incredibly complex and fascinating.
Well, I think we've thoroughly explored the world of fracking fluids today. We've covered it all, from the water quality and the clay control to the intricate workings of the crosslinkers and the breakers. We've even delved into the world of additives.
I hope this deep dive has given you a new appreciation for the science and engineering that goes into creating these fluids, and a better understanding of this important industry.
It definitely has, and it's a great reminder that there's always more to learn, even about the things that we might take for granted.
Absolutely. So keep asking questions, keep exploring, keep diving deep.
Couldn't have said it better myself. Thanks for joining us on this episode of The Deep Dive, and until next time, stay curious.